Okay, morning. Let's start the lecture. Okay. So we are going to talk about the key design now. Okay, just to follow up from the shaft design. Where do you see the key? Basically, on the shaft. Okay, and you will have a key seated here. So the key is going to be put inside the key seat. Okay. Yeah. And if you have the shaft is carrying a certain component, okay, so then and this is probably the hub, okay, and then the okay, it's just exploded here. So basically the case sitting right here, and this is the hub, okay, and this is the shaft, right? Yeah, so the case here, okay. Okay, there shouldn't be that much of a different a space between, but anyway, okay. So what does a K do, right? According to the definition, your K basically used to transmitting torque. A transmitting torque between the shaft and the hub. Okay, so that's basically what the K do. And when we pick the K, we essentially we'll look at the different Ks. Essentially we're basically looking at the size and the shape of the K. Okay. Okay. So that's basically what we do. There are two sets of standard generally for different Ks. You can take a look at lecture notes. Okay. Both of them are American National Standard. What was that? ANSI. What does I refer to again? American National Standard Institution, right? Yeah. So first, let's look at this. What's the types of K? Okay, types of Ks. So here's a diagram. Okay, I'll show you. But essentially, there's a parallel K, okay, and there is a taper case, and there's this so-called Woodruff K. Okay, these three types of Ks here. Okay, so here's a picture. Oh, so it's pretty big. First one is a parallel K. A parallel K includes so-called square K. So this is actually square here, looks like. Basically the width of the K the same as the height, and that's going to be the so-called square K. Okay, and then you have the length of the K, right? Typically, so you see here the K is sitting partially in the shaft. Okay, so typically the W, the width, is taking as 1/4 of the shaft diameter. Okay, so you don't want to be more than that. Okay, and we'll look at basically the different tables based on the standard as a proper. Basically, once you pick the W, so what will be a proper number for H, and this L. Okay, this L needs to be designed. So basically, this one needs to be calculated. And this one needs to calculate based on the loading condition, how much torque is being transmitted, and what's the safety factor we're designing, right? Basically, we have a design against certain kind of a stress condition. Okay? Yeah. For taper K, the difference basically it's a tapered surface. Okay, typically it's 1/8. Okay, 1/8 how much? 1/8. Yeah, 1/8 inch per feet. Okay, 1/8 inch per feet. There's one difference is sometimes there's no basically so-called head at here, and then this one here is so-called gib head. Okay, essentially it's a different application in terms of the assembling. Okay, so when you have a gib head key, it's easy actually to deassemble it. Okay, yeah, but you do have a sort of a standing out portion at here. Okay, so that might maybe cause an intrusion for some other machine elements. Okay, yeah. Oh, I need to turn on that the little red things here. Okay, so good. Okay, this is called gib head key, right? Yeah, and this is called the Woodruff key. Woodruff key is like a portion of a circular disk. Not necessarily half a circular disk. Okay, it's probably just a very small portion. Maybe the circle, you know, goes like this center, so it's just a portion of this. Okay, the difference is the Woodruff key is it generally will cut deeper into the shaft, right? Because this. Okay, yeah. Okay, so also does have a W and an H, you know, width and H for the Woodruff key and H. So basically, when you design, you're also designing this L here. Okay, if you pick these two keys. So we'll focus on this parallel key in this class. Okay, yeah, and so basically parallel square key are the typical things we'll be interested. Okay, so first let's look at the parallel key. Okay, parallel keys. So here's a table. This table is table 7-6. Okay, as a starting point here. Okay, this table 7-6 hopefully didn't change the table. So what does this table tell us? Okay, it tells us basically recommended for different shaft diameter. So for example, for shaft diameter from 5/16 to 7/16, it recommends your K width to be 332 and H to be 332. So that's recommending as a square K at here, right? Square K. And the K width depth is this much. It's basically it's the depth from here to here. K width depth. It's K width depth, as you can see, it's basically half of this H at here. So this is essentially just 1/2 H. Okay, so the square K, basically half of square K sitting in the K seat, and the other half is what is in the K weight of the hub. Okay, so when you design basically for the dimension for the K seat or the dimension for the hub K weight, and that's one thing that you need to stick to, right? Okay, yeah. So similarly, you have some other recommendations, but based on this second rule here, you have two recommendations. So you can either use this set or you can either use this set. So you can basically either use a parallel K or you can use a square K. So that's what the table 7-6 is telling you. Is that okay? Yeah. Now, if you don't like this table, and I do have another one in the lecture notes. This is another table. This is from the ANSI standard B17. Okay, yeah, very similar to the table of 7-6. Okay, so when you are within certain range of the shaft diameter, and what will be the width, right? What will be the height? And it has two, either square or rectangle. Okay. However, the standard does state pretty clear is here. It says values in non-shaded area are preferred. So what does that mean? So this is the shaded area, right? It's up to where? Up to, okay, this much here, right? 6.5. So basically, for shaft size less than 6.5, it recommends square K. And for shaft size greater than 6.5, we recommend, what was it? Parallel K, right? Or rectangular K. Okay? Yeah. So that's what this table tells you there. Okay, yeah. And here's another table. This is taken from Norton's textbook as one of our reference textbook. Okay, so this table is in my lecture notes there. Okay, what the difference is? Not much difference. Basically, giving a shaft diameter, but it does give a shaft diameter in terms of the standard unit millimeter, right? And the recommended certain K width and the height, right? What's good is it gives you, okay, a column here called set screw diameter. Now, because when you have a K, right? When you have a K sitting in here, then you have a hub on the top. Let's see, right? Yeah. Okay. So how do we basically fix the K at the location? So there's one structure is to use a set screw, okay, basically to fix the K, okay, on the shaft. Okay. So that set screw, right, also needs to be pegged properly. Basically, the diameter, the size of set screw. So this table here, okay, has this recommended set screw size. Okay. So in the lecture notes, there is a section on set screw here, but generally there's a lot of details. Okay, but anyway, so this could be one of your reference. Okay, so that's this table here. So you have 3 different tables, but they're all pretty much the same thing. Just the information slightly different from each other. Okay. So what are other considerations for case? The other consideration you should, or information you should know is most of the K, okay, stock case, okay, material, okay, they are low carbon cold-rolled steel. Okay, yeah. And second of all, okay, so when you machine the case, okay, your nominal dimension, okay, your nominal dimension should be negatively toleranced. So what does that mean? Basically, say that, for example, right, maybe you have a nominal size, basically the W, so-called 1/4 inch. Maybe this is a nominal size, okay, square K. Okay, square K. So basically, this nominal value of quarter, and this should be negative dimension. You will see that it's actually probably positive 0.000, and then negative 0.002 inch, like this. Okay, yeah. So why is that? Because you're going to put the K inside the K seat, right? So the K seat is machined using a tool. Okay, so if your nominal size is 1/4, then use a tool with, let's say, a 1/4 that kind of a size, and this, when this one is negative tolerance, so you can put the K easily inside the K seat. And the other thing is, if this is positive tolerance, and guess what? You have to hammer it into it, whatever, press fit into it. So that's already causing a stress on it, right? Beside the stress that we're going to design against, from the torque, from the compression. Okay, so that's something you have to bear in mind. Okay, yeah. A few more at here. Okay, so the maximum length of the K, okay, should be less than 1.5, okay, of this shaft diameter. Okay, it shouldn't be too long. Okay, if it's too long, right? If, let's say, when you design, you calculate the L, and the L is more than, so this is L, right? The L is more than this 1.5 diameter. So if that's the case, then maybe you should use actually 2 Ks. So have a 2 K seat separated by 180 degrees, for example. Okay, Yeah, so basically so I'll see use two cases or two case if necessary. Okay, that's basically the idea. And then the other thing is, so we're going to design for the K, for the L. So what do we design for the L against with, right? So design for the L, okay, is based on, so we're going to look at the details here. It's based on two different kind of stress. One is so-called shear stress, okay, and a bearing stress. Oops. Okay, so we'll look at the two different stress conditions. So one is shear stress on the surface, and the other is a bearing stress on the side surface. Okay. Yeah. Okay, so most important things that I think you need to bear in mind is, okay, the last bullet point. Okay, you don't want to assign an excessive safety factor for the K design. Okay, so no excessive safety factor, okay, for the K. So basically what it means is, you don't want to have a very long, because when you have a higher safety factor, you have a pretty long, basically a K, right? Yeah. Why is that? Because the K functions as a mechanical fuse. What you want is, you want the K to fill first, and you don't want your shaft or the hub to fill first. That make sense? Yeah. So that's the basically the idea here. Okay. So K functions as a mechanical fuse. Okay. Yeah. The K should fill first. All right. So those are basically, I think, a couple of bullet things for the K's here. Okay. And this is for rectangular K. Some of the bullets also works for other Ks. All right. And just a quick note on this Woodruff K. Quick note of Woodruff K. So this is the table 7-8, okay, from our textbook for Woodruff K. All right. Yeah. It gives us the K set width, okay, and based on the certain diameter of the shaft, right? Yeah. So within this range of the diameter, okay, here is W, okay, like this. So similar for other dimensions there. All right. Yeah. 7-7 is also for Woodruff K dimension. So it has a W, D, and B, and then there's offset E, okay, based on the shaft, K set depths for the shaft and the hub. Okay, so what are each one of these mean here? So let me show you the diagram here. Okay, so this is a dimension like this. Okay, yeah. So this is a K set. Okay, then you have a basically K height over here. You have a F. Okay, that's the basically that's the L. It's like the L we're indicated there, and you have a width. Okay, yeah, like this. So part of the K is sitting in the shaft. So basically within this range right here, this is a portion, okay, sitting in the shaft, and then the top one here, this is the portion sitting in the hub. Okay, yeah. Now, when you pick the K, you probably will see as a K number for the Woodruff K. You see, 202, 204, or like this, right? So what does the number represent at here, right? So the last two digits, okay, the last two digits is called This is basically saying the last two digits give the nominal key diameter in eighths of an inch. Okay, in eighths of an inch. So what does that mean, right? For example, if you have a A08, there is no 0808, but there is a 608. So let's say you have a 608. So the last digits is eighths of an inch. What does that mean again? It's an eighth. Mine is not working now. Yeah, this is a eighth. Yeah, so A times 1/8, right? A times 1/8. So this one here. So it give you A times 1/8. So we give you the 1 inch at here. The last two digits. Okay, and the first digits give you this so-called 30 seconds of inch. So 30 seconds inch, then it's a 30 seconds inch. So this is this one here should be 6 times 1/30 seconds. Does that give you 3 over? Yeah, that give you 3/16, right? Yeah. Okay, so that's the little trick here in terms of the telling the width and the B. What is the width? Width is W is this, and B is this guy here. Okay, yeah, B is this. That's how you can tell from here. Okay, yeah. Is that good? Yeah. So other dimensions are simply basically you see here. Shaft key-seat depth is this. Hub key-seat depth is this. So basically, the blue one is this. The red one is this top portion here. So these two numbers adding together should give us this total key height, which is this is C value here. Okay. Yeah. So if you do a quick addition in here, that's 0.104, right? Yeah. Okay. Okay, so anyway, so take a look at this table here. Okay, chances are you're probably not going to design for the key for using Woodruff key there, but you should be able to read the table, okay, to pick up a proper size if you're using Woodruff key. So what we're going to focus on is the key, basically parallel key. So I'm looking at let's look at the typical procedures for the key design. Okay. So first step, okay. So the key design, based on the shaft. So basically, you need to have the shaft diameter first, right? So what you need to do is you need to complete the shaft design first. Okay. So basically, the D is obtained. Okay. Then you start to select the key size from the table. Okay, because now you have a D based on table, you'll see that D is within certain range. Then you pick your W. That makes sense, right? So you pick your W as 1/4 of the D. Okay, based on the table there. Okay, yeah. So once you have the W, let's say if you design using a square K, okay, or parallel K, a rectangular, you will have the other parameter H will also be determined. Okay, depends. So once you determine this now, then you specify the material. And the material needs to be specified based on your material, the shaft and the hub. Because remember what I said, you want the key to fill first, right? So typically, most cases, you pick the key material to be less strong than the shaft or the hub material. Okay? So when you design, as actually the next step, you will see that. So when you design according to the minimum yield strength of the material. So there are three things in contact here: the hub, the shaft, and the key, right? So if your material for the key is the minimum, then you design based on your key material, right? Yeah, yeah.
For the purpose of this class too, should we consider the hardness of the key as well?
We don't.
Yeah.
Yeah. We don't need to. Yeah. Okay. So this is the next step right here. Okay. So in the design project, I think what I recommend is a 1020 cold roll steel. Okay. So the next step is basically determining this SYT, right, for shaft, hub, and key. Okay. So the next step, you design for the key now, right? For design the key. Now, if key is the weakest, okay, if key is weakest, then you complete the key design, right? According to actually what we said, right? Design, okay, to satisfy the two different stress conditions. One is the shear stress, right? The shear and the bearing stress. Okay, requirements. Okay, yeah. Now, but what you use is this time, because K is the weakest, so when you design, you're using the KSYT. Okay, you're using the case SYT for design. Okay, yeah. But somehow, let's say, I don't know what condition, but somehow you decided actually to pick K, the material which is stronger than the shaft and the hub. Okay, and if that's the case, right? So basically, if a K, right, is not the weakest, okay, so then when you design, right, so instead of using the case SYT, you actually would use whatever the smallest SYT is, between the three materials that here. Okay, yeah. So use the smallest SYT. Okay, yeah. So instead of basically design against the failure of the K now, you actually design against the failure of the shaft surface and the hub surface. Okay, yeah. So once you design this now, right, you're gonna basically pick the length. The length should be a nominal length. If your length end up with a 16 point decimal number 35 or something, you pick a nominal size. Okay. Pick the nominal size here. Your K, also you should bear in mind is the K length. Okay, the K length shouldn't be too long. Okay, shouldn't be too long. Actually, basically, it shouldn't be like the 1.5 diameter, right? Yeah, 1.5 diameter. It should also cover a certain portion, substantial portion of the hub. Okay, yeah. So in our design project, I noticed that in the past is the key actually turned out to be the lengths don't need to be very long, yeah. So that gives you certain actually maybe the freedom, in terms of the shaft length and also the face width of the gear. Okay. Yeah. Now the other thing is when you design your K, right? So let's say if this is a shoulder, okay. If this is a K seat, you're going to design it here. Okay. Make sure that the K seats, right, the location, don't run into the fillet location. So basically, you don't want the two stress concentration to merge into one location, right? So that's the K seat, right, location. Okay, K seat location. Okay, and the last of all, okay, is that actually I mentioned this. It's basically when you design, you make sure your key field first, right? Generally. Okay. Yeah. Yeah.
Is there ever a case where you want the key not failed first?
Not that I know of.
Or is this generally signature if there's ever a time that you
Yeah, that's what I'm saying. Mean, right? Maybe you can see all the time. Yeah, but I don't know. Actually, I can't think of a situation when you don't want the key to fail first. Yeah. So let's make it a general rule, right? Yeah. Yeah. Well, the spline is not a key, so we're designing a key here, right? So anyway, okay. So let's look at the key design parts, right? So what do we design for the key first? So first, we'll look at the design is the failure, okay, from shear stress. Okay. So here's the diagram of the key at here. It's sitting half in the shaft, half in the hub, and there is a force acting on the two sides of the surface, and the force comes from the torque, right? Yeah. So the shear stress basically is talking about is a shear stress on this surface here. Okay. So you have basically this is like a direct shear, okay, because this is pretty tight at here, okay, pretty tight, like a scissor cutting case. So this is essentially a direct shear case. Let's say the red part, if I looking into the details, right? So this is the area here, right? If we call this is AS at here, okay? Yeah. So AS, that's what we call the shear area. Okay. Yeah. So apparently torque is going to be the torque being transmitted. Okay. So F, right, is basically the amount of force that will generate the torque. So F times half of the diameter, which is the torque here. So that's why the F equal to T divided by half of the shaft diameter. Okay, so that's the F right here. Okay. So you have a force here, so the key pushing the hub or depends on the direction. So you basically have an action-reaction force on the key, right? Yeah. So let's say what will be the shear stress on this red area, on the shear area, right? Shear stress, we call that direct shear. So direct shear at here is F over this AS, okay? So the shear area, and F is T over D over 2, right? And shear stress area is rectangle area. So basically it's this side times this side here. And this side is width, right? This is the width. And that side is the total length. So times the total length at here. Okay? So then what does this equal to now? Equal to 2T over dWL. Okay? dWL. So that's the shear stress. And you wanted to compare the stress with the strains. So we're going to consider here is we consider there's a constant torque. Okay, constant torque here. Okay, so then we can use, let's say, the maximum shear stress theorem. Okay, maximum shear stress theorem. Maximum shear stress theorem says safety factor equal to 1/2 of this SYT and then over the maximum shear stress. Okay, maximum shear stress. So for this particular case, I mean, if you draw a stress element, and all you see is it's just a pure shear, right? It's a pure shear stress element. So basically, the tau max will be the same as this quantity here. Okay. So n is the safety factor. So n is generally be given by the user, right? If n is generally be given by the user, then we can see that the tau allowable is 0.5 like SYT over this safety factor n. Okay, that's the tau allowable. This is the tau allowable. This is the actual shear stress. So you don't want the actual one to be greater than this, right? and the boundary is basically set this guy equal this guy, and then let's see what we get, right? So when you set this equal to this and solve for L, okay, solve for L, okay, and what do we get? So L equal to 4nt over syt and dw. Okay, so that's basically the key lengths based on MSS theory for design against the shear stress, shear failure. Okay, is that good? Yeah, that's the first case. The second case is we want to design is the failure, okay, from this so-called bearing compressive stress. Okay, bearing compressive stress. So what does that mean is basically, bring it up here. You consider on the side of the shaft here. Okay, so the bearing, the key is sitting inside the key seat, and it's also sitting inside the hub here. So it's like being squished, right, by both the shaft and also the hub. Okay, so then on the side of the surface here, okay, on the side of the surface, it feel this force F, and this force F will cause this so-called the bearing compressive stress. Okay, yeah, we call it bearing compressive. This basically is a compressive stress. Okay, it's compressive. So the question is, how much of a compressive stress, right, existed here? So, for example, the top portion is sitting in the hub, so that's the compressive stress from the hub surface. Because action reaction force, so this should be the same, right? The bearing compressive stress is the same on this surface and also on at the bottom surface, right? That's from the shaft surface here. Okay. Okay, so how do we calculate this this bearing compressive stress? Okay, we can calculate this one here very easily. So this stress we'll call it sigma because it's a normal stress now. Okay, so if this shaded area here, okay, this area is, we call it AC. So that's the compressive stress area. Okay, okay, and then basically the sigma should equal to, right, F over AC. Okay, F over AC. And F is the same quantity as we calculated. So it's a torque divided by half of the diameter. And AC is this shaded area. How much is that? It's half of the length, half of the height. And then time the total length, right? Which is H over 2 and time T. Okay, times L. So totally you get 4T over, okay, DLH. That's the bearing compressive stress. And you don't want this stress to exceed certain strengths, right? So now the question here comes basically, here's a stress element, and you have the sigma acting on the top of that. If you draw a Mohs circle, basically, right, and this is the Mohs circle here, right, the Mohs circle. So if I'm going to use, let's say, MSS theory, okay, MSS here, and MSS, the n equal to 0.5 SYT over tau max, right? What's a tau max? So tau max is over here, and that tau max is actually equal to what? This is our sigma here, right? Tau max is actually half of this diameter here, isn't it, right? Yeah. So you plug it into here, okay, and then you can, just like a previous case, you can compare. Basically, we can see now sigma allowable is a 0.5 SYT over n, right? Sigma allowable actually, no. Sigma allowable is what? Tau max is half of this, right? Half of this. So sigma allowable, you put the 2 on the top, so that 0.5 is gone, right? Okay, that 0.5 is gone. So just sigma log of just SYT over N now. Okay, yeah. So you compare these two equations. Okay, set them to, there's no negative. Okay, set them equal to each other, and then solve for L. So your L turned out to be 4NT over SY and DH. Okay, SY DH. Is that good? Now, if you don't want to use MSA, you can also use von Mises stress, the DE energy theory. So you actually end up with the same thing here. Okay, if you use DE, your sigma prime, okay, is the same as sigma. Okay, you plug in the number, same as sigma. So then, DE is SY over sigma prime, right? It's actually turned out to be the same, same results. Okay, same results. So I got two equations for the L. Okay, one is for shear stress design, the other is for the bearing stress design. So, but if you look at this two at here, what's the difference? This is 4NT SYT DW. This is 4NT SYT DH, right? The only difference is H, actually, H and W. But if you're using a square K, then guess what? The same thing now, right? So if you're in a square K, basically it doesn't matter which criteria you're designing against. Okay? Yeah. But if you're using rectangular K, generally the H is less than W. Okay? If H is less than W, so it looks like which L is bigger? This one here, right? So the L from the compressive bearing stress is bigger than the other one. So then actually, which L would you pick? Would you pick this L or this L? The longer one or shorter one? The longer one, right? Yeah. So, okay, so that's just the minimum difference here. Okay. Yeah. SY. Okay. The SY at here. Remember that the design procedure. The SY here, you need to stick to the principle, which generally we don't really need to worry too much, right? But just in case, right? If you're picking the key material is stronger than the shaft, then that should be the smallest value, okay, among the three materials, okay, for the SY. Yeah.
Can you just pick a harder material and shorten the length?
Yes, you can. Absolutely. So that's actually a good, because basically if you turn out the length too long, right? So then you probably should pick a harder K-sit material. And that's probably one of the cases. If it's too long, then there's no way you can shorten it. So you just have to pick a harder material for the K, right? Yeah. But anyway, you can always consider a double K-sit, right? Yeah, to share the load. Okay. Okay. So let's take a look at a quick example right here. Okay. So let's say we're designing a square K. Okay. So shaft diameter we obtained is 25 millimeter. And the shaft is transmitting horsepower 15 kilowatts. And the shaft is spinning at 720 RPM. Okay. And we decided to pick a K. We decided the material already is 460 Newton millimeter square, megapascal. Okay. We're designing using a safety factor of 3. Okay, so that's the idea. So let's say what would be a proper K length L, right? So first you need to determine how much torque is being transmitted, and torque is equal to H over W, okay, and it's approximately 9.55 and H over N. So plugging all the number, you get Okay, 198.9 Newton meter. Okay, Newton meter. Now, because the key material is in millimeter square, actually it's easier to do the calculation if you convert that, okay, into a Newton millimeter, okay, for ease of calculation. So that's your T, right? Okay, so then we'll look at the both case, but actually you don't really need to. We'll look at what's the tau allowable. And tau allowable is 0.5 SYT over N. Okay, so this gives us this much. We can also look at sigma allowable, so the allowable shear stress and allowable bearing stress. Okay, that's SYT over N. Okay, so this turned out to be this number. Okay, yeah, that's it. Okay, so then time to pick the K now. Okay, we're deciding for the square K, so their W should be the same as H. So we pick, okay, half of the diameter. So that's 6.25 now, okay, based on the given D. Okay, 6.25 is not an integer number, so I think we want it to wind up into an integer number. At this stage, you can wind it down instead of winding it up for the W. Okay, because why? Because you're designing for the L, right? So the L length can compensate the deduction at here. Okay, yeah. So we pick a 6 millimeter from the table 7-6. I'll show you the -6 there. So now it's the time for the L, right? So now if we decided, so L, because it's square case, so really doesn't matter which formula you use, but we can use this formula, okay, for calculation of L. So plugging all the numbers, and this turned out to be 34.6, okay, millimeter. Okay, 34.6 millimeter. Okay. Now this is not integer either, so you should bump it up to 35 millimeter. Okay. Yeah. So this one you don't bump it down now, right? You move it up. Okay. Yeah. So then overall, what's the key size? Is 6 by 6 and time 35 millimeter here. Okay. Yeah. So that's the typical procedure of designing for the K. Okay. I think it's pretty straightforward. So up to this stage now, your design project, you can actually, beside the bearing, we should be able to finish that shortly in the next week, okay, or two. Then you can fully get started here, okay? So who doesn't have a group yet for? So can I put you guys together? Yeah, Will and yeah, okay. You talk to each other. Oh, there's one more here. Can I put you guys together? Yeah?